Hello and welcome. In this video we are talking about moments, and by moments we just mean the turning effect of a force. So any force that's causing an object to turn is likely to be what we call a moment. Now an example would be something like a spanner turning a nut, and on this there's a couple of labels that we could add. The first one is the word pivot, and pivot is just the point around which the whole thing turns. Also over here we have a force, and we often also talk about a distance between the force and the pivot point, but we'll talk about that in a bit more detail in a minute. Another example that you might see would be something like a door handle. I'm sure you can think of lots of examples yourself, but another one is a door handle. We have the pivot point, which would be around about here, and the force down here, which would cause a turning effect in the anti-clockwise direction. And yet another example would be something like a lever. This is called a lever, and levers are often described as force multipliers. And a force multiplier means that we have a small force on this side and that creates a larger force on the other side, so we can use a lever to maybe lift heavy loads or open lids or things like that. So a lever is a force multiplier, and it uses the idea of moments. Now you should be able to actually calculate a turning effect or a moment, and you could do it with an example something like this. Now we need an equation, and that equation is given to you in the exam, and it goes like this: m equals f times d. They tell you that m is the moment of the force, F is actually the force, and D is the perpendicular distance from the line of action of the force to the pivot. So that just basically means a distance from the pivot to the actual force. It has to be perpendicular, so what that means is if you have an example like this, the distance isn't actually from the pivot to the force in this direction, it's actually in the direction with the line of force and perpendicular to the pivot, so it would actually be in this direction here. So if we know the data that we have here, we can work out the moment, and the moment is just simply force times distance, and the force here is 20 newtons, which you can see here, times the distance, which is here, and the answer is 60. Now you're not given the units here, so you must know that and remember the units. For force it's newtons, for distance it's meters, and for moments it's Newton meters, written like this. Okay, so it's important to remember that because you might be asked to note it or write it down in an exam. Okay, so it may be worth trying a couple of examples yourself. Here are two questions that you can try. You can pause here, give these a go, and I'll go through the answers when you're ready. So for this one here on the left, we have moment equals force times distance, and the force we can see is 100 newtons. The distance is 0.25 meters, so the moment is 25 Newton meters. For the door handle it's 20 times 0.1, and that will give us an answer of 2, and again units Newton meters. Okay, so that's a couple of examples of where you might use the idea of moments, but what we also need to think about is when we have moments not just on one side but on two sides. So here's a very simple example. We've got our pivot point here, not pivot, pivot point here, and we have two objects causing a force in two directions. Now the two directions are what we call the clockwise moment, so that just means the turning force in the clockwise direction, and on the other side it's the anti-clockwise moment, so it's the turning force on the anti-clockwise side. And for any object that is balanced, these two must be the same. So if the anti-clockwise moment equals the clockwise moment, the object is balanced. And you can see then that if we try and do that mathematically, I've put in some numbers here. What's the moment on the anti-clockwise side? Well, we know how to work out moments now. It's just the force times the distance, the perpendicular distance, so it's 20 times 2 over here, and same on this side, 20 times 2, and both of those values are 40 Newton meters. So both of the turning forces are the same, and therefore this thing is balanced. I should have written there 40 Newton meters. Right, so sometimes we have a situation where the two distances might be different, and we can see what happened in this scenario. So on our anti-clockwise side, we have the force of 20 times a distance of 1, and that gives us 20 Newton meters, and on this side it's the same as before. We have 20 times 2 equals 40 Newton meters, so we can see the clockwise moment is larger than the anti-clockwise moment, so this thing is now unbalanced, and it will topple over or tip over in the clockwise direction. Now if you are doing the higher tier, you are going to be required to actually work out either a missing distance or possibly a missing force. So here we have a distance d that we don't know, and we can use this idea of clockwise moments and anti-clockwise moments having to be equal for a balanced object in order to work out d, and this is how we do it. We know if this object is going to be balanced or is balanced, that the anti-clockwise moment must equal the clockwise moment. So let's work out the values that we can. We can work out the anti-clockwise moment, and that goes like this. It's a force times distance again, so it's 20 times 1.5, and on this side we have a force of 40 newtons times a distance that we don't know. So these two have to be equal for this thing to be balanced, and we can just plug in what we know here. So this side is 30, 20 times 1.5 is 30, equals 40 times our distance. So if you are good enough at maths, you can just rearrange this a little bit, and the way we do that is we divide everything by 40 in order to get rid of this 40 on this side. So we'll end up with 30 divided by 40 equals d, and therefore 30 over 40 is 0.75. That means our distance is 0.75. Don't forget the units, it's in meters. So we can check this by plugging it back into our example over here. So if that's 0.75, we need to make sure that the clockwise moment is the same as the anti-clockwise. We know the anti-clockwise moment is 30 Newton meters, and so if we look at this, 40 times 0.75 is actually 30 Newton meters. So this is correct because this thing now balances. What I've got here is a couple of examples. There's one here and one hidden over here. So we've got a couple of examples. You can try these out, see if you can calculate the value of x over here, and see if you can calculate the size of the force created by the counterweight on this crane. So we've got a distance of 5 and a force of 10,000 newtons, a distance of 1 on this side, and a counterweight that creates a force. See if you can figure out what that force might be. So maybe pause here, try them out, and then I'll go through them when you're ready. So for this one over here, where we've got two people balancing on a seesaw or a beam, we know we can work out the clockwise moment. So we've got 500 times 3 on this side, and on the opposite side we've got 750 times x. If we tidy that up a little bit, we've got 1500, 750 times x equals 1500. Divide both sides by 750, so we have x is 1500 divided by 750, and that gives our x, which is our distance, of 2 meters. Don't forget the units. We can plug that back in. Does it work? If we put a 2 there instead of the x, the anti-clockwise moment would be 750 times 2, which is 1500, which is what is the clockwise moment. So this thing balances. This answer is correct. Here we have our crane, so let's calculate clockwise moment. We have 10,000 times 5, and a force, we'll call that F, times 1. So F times 1 equals times joules. What did I put that for? Oh no, times 5 that says, yes. So let's tidy that up. That's even worse. So 10,000 times 5 is 50,000. So F times 1 equals 50,000. This is slightly more straightforward. We know if something times 1 has got to be 50,000, that means our force is going to have to be 50,000 newtons, and in this case the unit is newtons. So that's the force of the counterweight over here. Now remember, being able to calculate the missing values is part of the higher tier, but other than that, that's an overview of moments. It's just a question of looking at many practice questions as you can, and then you'll become quite familiar with it and become quite good at using moments. But that's me done for now. Thanks for watching, and I'll see you again soon.